Hello students, welcome to the course of Data Communication and Networks. I'm your course instructor, Dr. Munir Ober. In today's lecture, we will be studying about multiplexing. We know that devices use a medium for connectivity, and we also know that the bandwidth of this medium can be shared among multiple devices. So the today's lecture is about the techniques for sharing this single link among multiple devices. This is actually known as multiplexing. These are the contents for our today's lecture. First, we will study about the multiplexing, the basic concept about the multiplexing. Then we have two major types of multiplexing. The first one is frequency division multiplexing. This is used for analog signals. Then we have time division multiplexing. This is used for digital signals. In the time division multiplexing or TDM, we have two types. The first one is synchronous time division multiplexing, and the second one is statistical time division multiplexing. So we will look into all these with some example questions and their solutions. Multiplexing. In general cases or in general scenario, we say that two devices are connected or two devices use a single medium for connecting each other or single link. So this link is used by a single device at a time, or for full duplex, this single link is shared among both the devices for communication. So if we have multiple devices connected to a single link, then we have two options. The first one is that each device must be given a portion of time, so that in that time the device may occupy the link, or we can say that this link can be shared among all the connected devices. So multiplexing actually deals with the sharing of link among the connected devices. Under the simplest conditions or general conditions, a medium can carry only one signal at any moment of time. For multiple signals to share one medium, the medium must somehow be divided, giving each signal a portion of the total bandwidth. So this medium is divided among all the devices, and the bandwidth of this medium is shared with these connected devices. So this is known as multiplexing. Whenever the bandwidth of a medium linking two devices is greater than the bandwidth need of the devices, the link can be shared. So if we don't share the link, then it would be half duplex or simplex. So for full duplex, we need the link to be shared among the devices. We are talking about two devices. There might be multiple devices on a single link. So for that case, also the multiple devices will share the common link. Multiplexing is the set of techniques that allow the simultaneous transmission of multiple signals across a single data link. Multiple signals across a single data link. So we have only one link, and on that link, multiple devices are sending or transmitting their data by using their signals. So definitely there would be multiple signals on a single link. As the data and communication use increases, so does traffic. So the communication and data is increasing day by day. The number of nodes is also increasing, so the traffic from the devices or nodes is also increasing, and for that purpose the multiplexing is the only solution to let the connected nodes share a single medium or limited medium among them by giving multiple signals. This figure shows the dividing of a link into multiple channels. We have a single link or single medium between multiple devices at both ends. At one end, we have n number of input lines, These are actually the hops or hosts or devices which are connected to a multiplexer. So the signals from these devices are combined, and from here different channels are created in a single medium and transmitted at the same time. At the other end, at receiving end, the multiple devices which are connected to a demultiplexer receive the data from these devices. So the demultiplexer takes the data from a single link having n channels, and according to these channels divide the data and forward the data toward the corresponding ends. Multiplexing: two or more simultaneous transmission on a single circuit. Simultaneous transmission on a single circuit. The categories of multiplexing: we can divide the multiplexing into three main categories. The first one is frequency division multiplexing, FDM. The second one is wavelength division multiplexing, WDM. And the third one is time division multiplexing, TDM. The first two are used for analog signals. We have already studied about the types of signals, and this one, TDM, is used for digital signals. So the TDM is actually used for digital networks, for our LANs, for our computer networks, and these two can be used for any communication system. In this lecture, we will study about the FDM and TDM. The WDM is not in our course, so we will not discuss this one. First, frequency division multiplexing: assignment of non-overlapping frequency ranges to each user or signal on a medium. So what happens in FDM? Each user is given a particular frequency range, and that range doesn't overlap with the range of any other device in the network or any other device connected to that multiplexer. Thus, all signals are transmitted at the same time, each using different frequencies. So we have different nodes, and each one is given its own frequency, and that frequency range doesn't overlap with any other range. So in that case, these all signals can be transmitted at the same time. A multiplexer accepts inputs and assigns frequency to each device. Now if you look into this diagram, here we have multiple devices at one end, and at the other end we have also some devices connected to multiplexer and demultiplexer. The link is divided into multiple channels. Now here, if we look into this figure, we have the division of frequencies. We have computers connected to a multiplexer, and this multiplexer can multiplex the signals of these devices connected. So for each user, a range is given, a range of frequency is given. For PC1, let's say we have channel number 1, it starts from 2001 to 4000. The second one channel starts from 4001 to 6000, and so on. So these are non-overlapping frequency ranges assigned to different devices. On the other hand, we have this multiplexer, and this multiplexer can also demultiplex the combined frequency, which has different channels of different frequency ranges which are non-overlapping, and these can distinguish the data received from these devices. So a multiplexer is attached to a high-speed communication line. At both ends we use a multiplexer. This demultiplexer also works as a multiplexer if these devices want to transmit data. A corresponding multiplexer or demultiplexer is on the other end of the high-speed line and separate the multiplexed signals. So this one, multiplexer or demultiplexer, separates these channels from the line and forward the data to corresponding devices. The frequency division multiplexing is used for analog signals. Analog signaling is used to transmit the signal. Broadcast radio, television, cable television, and the AMPS cellular phone systems use frequency division multiplexing. Now, if you look into the cable TV, we when we tune the channels, we find different ranges for different TV channels. So all these channels are transmitted on a single coaxial cable, and here we tune their frequencies and get these different channels on our TV. This technique is the oldest multiplexing technique. This is actually the initial multiplexing technique, and this was introduced for the radio and television systems, and later this was also used for AMPS, the first generation cellular networks. Since it involves analog signaling, it is more susceptible to noise. We have already studied the impairments, so the noise is more effective on such type of signals because these are continuous signals, and continuous signals are more susceptible to noise. FDM, the frequency division multiplexing, is an analog multiplexing technique that combines analog signals. We would have multiple users having multiple signals, and user 1, user 2, and user 3. Let's say there are 3 signals and these are different from 3 users. So what happens? These signals are combined together and transmitted. So this method is called frequency division multiplexing, and this is used for analog signals. So we have 3 baseband analog signals. These signals are modulated by using modulators, and some frequencies are created. So we have now 3 type of different frequencies. After that, these 3 frequencies are combined by using a multiplexer having the technique of FDM, frequency division multiplexing, and a single signal is generated on the link. Now this single link has multiple signals multiplexed together, and receiving end we will have another multiplexer or demultiplexer like this one. Here we have demultiplexer, and we got a combined signal having multiple signals, and all the signals are not overlapping with each other. So if they are not overlapping, then we can use a filter to filter out a particular signal, just like when we tune the TV channels. So we give a particular frequency, and on that particular frequency we get some particular TV channels. So filters are used, and after filtration a demodulator is used and the base band signal is obtained. We have multiple examples in this lecture, so we are starting with example number 1. Assume that a voice channel occupies a bandwidth of 4 kilohertz. So for voice channel we need 4 kilohertz. We need to combine 3 voice channels into a link of bandwidth of 12 kilohertz. So 4 kilohertz multiplied by 3 voice channels equals 12 kilohertz. From 20 to 32 kilohertz, so the range would start from 20 and would end on 32. Show the configuration using the frequency domain. Assume there is no guard band. Actually, when we combine these signal, we use one additional signal of small size, and that signal is used to avoid any sort of overlapping among the signals. That signal is known as guard signal. So there is no guard signal since we need 12 kilohertz. and the range is also from 20 to 32, so there is no space for guard band. Solution: we shift modulate each of the three voice channels to different bandwidth. These voice channels are from 1 to 4, and we would change this from 1 to 4 to some values between 20 to 32. We can check this in the figure. For 1, 2, and 3 users, the bandwidth is 4 kilohertz from 0 to 4, and now we would change this to a value between 20 to 32. So for the first, we are modulating it to some new ranges, and these ranges are from 20 to 24. For second user, we are starting with 24, ending with 28, and then from 28 to 32 is given to the last user. Now, if you look into these ranges are not overlapping with each other, so we can easily combine these. So we will have a bigger frequency starting from 20 and ending on 32. In between, we have these small frequencies for these users. We use the 20 to 24 kilohertz bandwidth for the first channel, as we did here. Then 20 to 28 kilohertz bandwidth for the second channel, this one, and then 28 to 32 kilohertz bandwidth to the third one, this one. And after that, we combine all these and get a multiplexed signal starting from 20 to 32, having all these frequencies or all these bandwidths. At receiving end, these are filtered and then demodulated, and the base frequencies or the base ranges are obtained, which are of 4 kilohertz. Then we have example number 2, 5 channels, 1, 2, 3, 4, 5. 5 channels, each with 100 kilohertz bandwidth, 100 kilohertz for each, are to be multiplexed together. What is the minimum bandwidth of the link if there is a need for a guard band of 10 kilohertz between the channels to prevent interference? Now, if you look into the figure, here we have a bit space of 10 kilohertz, again 10 kilohertz, 10 kilohertz, and 10 kilohertz. So these are actually for the guard band. These 10 kilohertz slots are used for separating the 100 kilohertz bandwidths, and the total bandwidth is 540 kilohertz. So the solution: for 5 channels, we need at least 4 guard bands in between. If there are 5 channels, so in between there would be 4 guard bands. This means that the required bandwidth is at least 5 into 100, 100 plus 100, 100, 100, 100. So 5 into 100 plus 4 into 10. So 5 channels, each having 100 kilohertz, and 4 guard band, each having 10 kilohertz. So this will give us 540 kilohertz. Example number 3, 4 data channels, digital data channels, each transmitting at 1 megabits per second, use a satellite channel of 1 megahertz. Design an appropriate configuration using FDM. Now here we have 4 data channels. Each having 1 Mbps, megabits per second, and the satellite channel is of 1 megahertz. So this one is of 1 megahertz. So we need to combine all these for 1 megahertz. So here what we do, the satellite channel is analog and our system is digital. We divide it into 4 channels, each channel having a 250 kilohertz bandwidth. Each digital channel is of 1 Mbps in modulated, such that each 4 bits is modulated to 1 Hz. One solution is 16 QAM modulation. QAM is the quadrature amplitude modulation. It can be 8, 16, 64, 128, and 256. So by using 16 quadrature amplitude modulation, we convert each 4 bits into 1 hertz. Now if you calculate this, then 1 megabits per second would need 250 kilohertz. 250 for the 4 users, and multiplex these all by using the frequency division multiplexing. And if we combine all these without any guard band, it would be 1 megahertz, and this one is transmitted towards the satellite. In frequency division multiplexing, we can also implement the analog hierarchy, in which we will have multiple multiplexers at multiple levels. Now here if you look into this diagram, here we have 12 voice channels connected with an FDM, and here these 12 are multiplexed and these are further connected to another FDM. So these 12 are making 48 kilohertz channel, and which is connected to another FDM. So this FDM is taking 4 more groups just like this one. So there would be some other channels to coming to this FDM. After that, these will be connected to this FDM, each having 48 kilohertz, and all these would be combined to form a 240 kilohertz channel. And after that, in hierarchy, we will have third FDM and so on. So this can be implemented at different levels. We will have multiple FDMs, and these FDMs will be implemented in a sort of levels, in which each FDM will be connected to another super FDM, and after that super FDM, and so on. So ultimately one FDM will combine a big number of channels in different hierarchies. We have one another example for frequency division multiplexing. It's example number 4. The advanced mobile phone system AMPS uses 2 bands. The AMPS is the 1G first generation cellular phone, and this was before the GSM. The AMPS uses analog signals, and for multiplexing it uses FDM, frequency division multiplexing. So it uses 2 bands. The first band of 824 to 849 megahertz is used for sending, and 869 to 894 megahertz is used for receiving. One for sending and second range is for receiving. Each user has a bandwidth of 30 kilohertz in each direction. How many people can use their cellular phones simultaneously? We have a range from 824 to 849 megahertz, 25 megahertz range for sending, and 25 megahertz for receiving. This is in megahertz. Now each user has a bandwidth of 30 kilohertz. not megahertz, kilohertz in each direction, 30 plus 30. How many people can use their cellular phones simultaneously? At one time, how many people can use cellular phones? Now, solution. Each band is of 25 megahertz. If we divide this 25 megahertz by 30 kilohertz, we get 833.33. In reality, the band is divided into 832 channels. Of these, 42 channels are used for control, which means only 790 channels are available for cellular phone users. So if we divide 25 megahertz by 30 kilohertz, we get 832. And out of this 832, 42 channels are used for control. So if we subtract this 42 from 832, we get 790. So 790 channels are available for cellular phone users. Means that 790 people can simultaneously use their cell phones connected with the amps network having these ranges of frequencies, and each user using 30 kilohertz. Next is time division multiplexing. Sharing of signal is accomplished by dividing available transmission time on a medium among users. This is used for digital signals, and for analog signal we don't use time division multiplexing. In time division multiplexing, each user is given a particular period of time to transmit the data. So we will have different time slots for different users in time division multiplexing. Here, if you look into this figure, we have four users connected with a multiplexer. These are identified by 1, 2, and 3, 4. In the channel, each user is given a particular period of time. So if you look into one is given a time, then after that 2, 3, and 4, and again 1. So 1 must send some data, and after that wait for 2 and 3 to take their time slots. Once they complete, again 1 will be given the time slot, and at receiving end demultiplexer read these time slots. Actually this must be synchronized with this multiplexer, and the time slots are utilized or forwarded to their corresponding destinations. Time division multiplexing comes in two forms. We have two forms of time division multiplexing. The first one is synchronous time division multiplexing, and the second one is statistical time division multiplexing. This one is also known as asynchronous time division multiplexing. First, synchronous time division multiplexing. The first one, the original time division multiplexing. This is actually the original time division multiplexing which we have studied now. The multiplexer accepts input from attached devices in a round robin fashion and transmit the data in a never ending pattern. The T1 and ISDN telephone lines are the common examples, and these two use synchronous time division multiplexing. Here we will have some users, and each user would be given some time slots. So if you look into this one is coming from A. So A is given some time slots, A1, A2, and A3. Similarly for B, we have B1, B2, and B3. Now if we look into the frames, in each frame A is given some time, then B is given some time, similarly C. So this one is a complete time slot duration for 3 users. So each user is given a time slot, and in this way the communication channel is shared among different users. Here we have another figure. Here we have 4 devices connected with a multiplexer, and if we look into these bits, suppose we are sending 1 bit. The time for transmission is taking only 1 bit from each user. So the first bit is from 1, then second bit is from 2, 3, and 4. It is completed. So again 1 will start, and similarly this cycle will continue until these devices stop their transmission. If one device generates data at a faster rate than other devices, then the multiplexer must either sample the incoming data stream from that device more often than it samples the other devices, or buffer the faster incoming stream. So we have 2 options. The first one is to give more slots to the speedy device, or to use a buffer at receiving side, so that that buffer can store the data from a speedy device, or device which is rapidly generating or sending data. So here in this figure we can see that the device A is sampled twice here. So given it has been given 2 time slots, and rest of the devices are given only 1 time slot. If a device has nothing to transmit, the multiplexer must still insert a piece of data from that device into the multiplexed stream. This is the disadvantage of synchronous time division multiplexing. It is a sort of limitation for STDM, the synchronous time division multiplexing. Here, this device is active, the rest of 3 are not active. So what happens, for each device there's a time, and if we look into the data, first block is okay. In this time slot, number 1 sends data, and the rest of the time slots are empty because these 3 devices are idle. They are not sending any sort of data. So only one input device is transmitting data, and rest of the time slots are sending zeros as idle data bits. We have an example for synchronous time division multiplexing. This is the figure. Here we have 3 users, A, B, and C. So now consider this figure. The data rate for each input connection is 3 kbps. So data rate for this one and the third one is 3 kbps, 3 kilobits per second. If 1 bit at a time is multiplexed, a unit is 1 bit. What is the duration each input slot, each output slot, and each frame? So here, what is the time for this one, this entire frame, and this single block in the frame for device A? So the first, each input slot, the data rate of each input connection is 1 kbps. This means that the bit duration is 1 by 1000 or 1 millisecond. The duration of the input time slot is 1 millisecond, same as the bit duration. So here this one is 1 ms. Then second is each output slot. The duration of each output time slot is one third of the input time slots. Since we have 3 users, so it would be divided by 3. This means that the duration of the output time slot is 1 by 3 milliseconds. This one or this one or this one, for each user we have 1 by 3 milliseconds. Then the third one is each frame, the time for each frame or the duration of each frame. Each frame carries 3 output time slots. So one is 1 by 3. So for 3 output time slots, it should be multiplied with 3. So the duration of that frame is 3 into 1 by 3 milliseconds or 1 millisecond. So the duration of a frame is the same as the duration of an input unit. So duration for this frame or this one or this one, it would be 1 millisecond. Next example, the example number 6. The next figure, here we have a figure. We have 4 users, each having 1 Mbps. In the next figure, synchronous time division multiplexing is shown with a data stream for each input and one data stream for the output. The unit of data is 1 bit. 1 bits are given in each unit in the frames. The input bit duration, find the input bit duration, the first thing. So first check this one. The input bit duration is the inverse of the bit rate, 1 megabits per second. So the duration should be 1 divided by million, 1 microseconds, or 1 millionth part of a second. So this would be the duration for input bit. Here duration for the input, this one bit is 1 millionth of second or 1 microsecond, also for all these bits. Then the output bit duration. The output bit duration is 1/4 of the input bit duration, that is 1 by 4 into million, 1 millionth of second, 1 by 4 into mu second. It would be these bits, all these bits in the frames. These are actually time slots. Then third thing is the output bit rate. The output bit rate is the inverse of the output bit duration. The output bit duration was 1/4 mu second, so it would be 4 megabits per second, 4 Mbps. This can also be reduced from the fact that the output rate is 4 times as faster as any input rate. So the output rate is 4 into 1 Mbps. Actually here we have 1 Mbps for input bit rate, and for the output bit rate it would be 4 times greater than the input, so it would be 4 Mbps. This one, entire frame. also all these 4 frames. Then last thing is the output frame rate. The frame rate is always the same as any input rate. So the frame rate is 1 million frames per second. We have here 1 megabits or 4 megabits, then it should be 1 million frames per second. Because we are sending 4 bits in each frame, we can verify the result of the previous question by multiplying the frame rate by the number of bits per frame. So if we look into the previous question, this thing can be solved by taking the previous example. So this was about the synchronous time division multiplexing. Now we are moving towards the statistical or asynchronous time division multiplexing. Statistical time division multiplexing. A statistical, a statistical multiplexer transmits only the data from the active stations. Actually, there was an issue with synchronous time division multiplexing, that was here. If some systems are idle, still there were some time slots assigned to them, and this was actually the wastage of the entire bandwidth or the time slots during the transmission. So to avoid such type of case, we use the statistical time division multiplexing. If a workstation is not active, no space is wasted on the multiplexed stream, because the time slots are given only to the active stations. Creates a frame containing only the data to be transmitted, and no empty slots are used during the transmission of data. In empty slots, usually we put zeros, so there would be no dummy zeros during the transmission of data. This is the comparison between the synchronous TDM and statistical TDM. Now, if we look into the lines, here we have 5 lines. The line A is transmitting A1 only 1 block of data, B is transmitting 2 blocks, C is transmitting nothing, this one is idle. Now here A is given time slot and this one got empty, but still it is assigned to C, and here to E, this one is empty because at this time it is not sending something. Later it sends E2, so next time this one is filled. A is not sending something, so this one is empty. Now similarly for C, this one is empty. So these slots are wasted in synchronous time division multiplexing. Now if you look into the statistical time division multiplexing, here we don't have any empty slot, but there is one additional thing that identify the generator of slot or the owner of slot. So here the order was understood that first slot is for A, second slot is for B or must for B, then third slot must be for C. So this was actually understood, this order was understood. So here the order is not understood at the receiving end. So for that purpose, one additional flag is also attached with the packet or the slot that identify the owner of the slot or the sender of the slot. So here A1 is generated by this one is identified, then B is identifying line B, similarly D is identifying the line D. So this is the main difference between synchronous and statistical time division multiplexing. To identify each piece of data, an address is included. Here we can see that the addresses are included with these pieces. So we have data of A, then address of A, similarly data of C and address of C, and so on. If the data is of variable size, a length is also included. It is possible that we don't use fixed slots here. So for that purpose, we must also provide the length of that block here with the address. So it would be like this: data of A, length of A, and address of A. So this whole thing would be about line A or the device A. This type is better than synchronous, so it doesn't require a line over a high speed. The statistical time division multiplexing does not assume all sources will transmit all the time. We have seen this thing that it doesn't use any empty slots or doesn't entertain the idle systems. Since it is efficient, therefore it is good for low bandwidth lines, and usually it is used by LANs. So we can say that the statistical time division multiplexing is using the bandwidth in an efficient way. So this was all about multiplexing. If you have any question, you can put your questions in the KCMS. Thank you.